Welcome to part 2 of lecture 6 of Bluff Body Aerodynamics. Now that we've done a basic introduction to acoustics, let's get into the automotive aspect. Specifically here, we're going to be talking about aeroacoustics, which is flow-induced sound. And this happens due to both periodic and random fluctuations in the flow field, so from turbulent flow and also from flow separations. Aeroacoustic noise sources are mostly relevant at highway speeds where the flow-induced sound can dominate over other sound sources that occur, like, for example, the tire road interactions or engine noise. And so we can see that here. If we consider sort of a typical vehicle sound pressure level frequency spectrum at a driving speed of 50 kilometers an hour, we basically have an on-road test, which is this dark blue, sort of the top line. And if we look at the drivetrain noise, which is essentially the noise from the engine, transmission, etc., that's the green. We can see that over most of this frequency range, this is the biggest contribution, and it's almost the same as this dark blue line. And all the other sources, including wind noise, are much lower. But if we go to a very high vehicle speed, this is almost excessive. I don't really know when anyone ever be driving this fast in a regular car, but at 160 kilometers an hour, again, we see the same sort of breakdown of the noise into various sources, and what we see is that the wind noise is the dominant feature and sort of is almost equal to the total noise from an on-road test across the entire frequency range, except for at sort of the very lowest frequencies. Now, there are three fundamental types of aerodynamic sound sources: monopoles, dipoles, and quadrupoles. Here, these show how the sound intensity associated with each type of source scales with the flow velocity. Now, we haven't really introduced sound intensity. It's basically a directional quantity, but the sound pressure scales with the intensity. And what we see, the important thing is that the dependence on the sort of speed of sound factor changes, but that's sort of a constant for a given flow conditions. But then sort of the velocity factor changes a lot. So for a monopole, we have v to the 4 power, v6 to the 6 for dipole, and v to the 8 for a quadrupole. And the way in which these sources radiate is also different. So a monopole is essentially a pulsating. You can think of it, if you imagine like a sphere that was just pulsing in and out, that's a sort of ideal monopole source. And it's going to radiate uniformly in every direction. A dipole is typically caused by time-varying force on a surface or time-varying pressure on a surface. And this tends to have sort of an axis of silence and then sort of radiates sort of in a ring around that. And a quadrupole is typically caused by turbulent fluctuations in the flow, and it has sort of two of these axes of silence, and then sort of, you can imagine sort of two rings that cross each other in 3D space here for the radiation pattern. So just to reemphasize this, the monopoles, which are often called mass sources, this can be caused, for example, or approximated by unsteady flow in and out of an opening, so leaks and seals, and the exhaust pipe outlet noise would be examples of monopoles. Dipoles, or impulse sources, again, are caused by time-varying pressures on surfaces. This will be caused by either free or separated flows. And then quadrupole or volumetric sources are caused by turbulent flow, either in shear layers or in vehicle weights. Also, as I mentioned, again, just to sort of have a little bit more detail, the sound sources radiate differently. The monopole, basically, you get this equal radiation in all directions. The dipole has this sort of one line of silence, and quadrupoles have two. Again, to emphasize how these things scale differently, we saw this already. But note, again, the inverse scaling with speed of sound to the various powers. So the magnitudes of these sources tend to be smaller for quadrupoles compared to dipoles, and for dipoles compared to monopoles, unless the velocities become very high.